Okay, sorry about that. The camera just went off on my computer, and so I'm just going to start where I was. Basically, we had talked about c being the speed of light, and we talked about if we have a person here shining a flashlight, a person here shining a flashlight, so that we have beams going this person right here on the ground, these people all in the same frame of reference. Everybody's going to see c as being the same thing. Just a second, let me get this stuff off of here. I don't know if you can see that or not, but all right. But if this train, if we put this in a train and we move this at 1/2 the speed of light, 1/2 c, so this is going this way, what will this person see? Well, sorry, my computer keeps bringing stuff up, and I don't know if you can see that on your screen. So, well, you would say, well, this person, this beam of light is going to be going at 1.5 c, and this beam of light is going to be going at 1/2 c. And what Michelson-Morley found out is that is not true. In fact, it makes absolutely no difference what the frame of reference is. To this observer, this beam of light is going at the speed of light, and this beam of light is also going at the speed of light. It would be as if the motion of the train didn't matter at all. Let me show you this in a little bit of a more bizarre way. And that is, imagine that you had a spaceship out in space and another spaceship coming toward, I know that's not a very good spaceship, and there's a flashlight on top of this spaceship and a flashlight on top of this spaceship. Okay, if this spaceship is sitting here and this one's stationary and we shine a beam of light, this one's going to see the light leaving at the speed of light, this one will see it coming at the speed of light. What happens if they're moving toward each other? Let's say they're moving toward each other at the speed of light, or at 1/2 the speed of light. This person will see this beam of light approaching at c. Doesn't matter that they're closing the gap. And this person, if this one shines his light, the same thing. This will be at c. Here's an even more bizarre one. If this is going this direction, and let's say he shines a beam of light this way, but he's traveling at c. Now, if this was a train car, if you were to shoot a ball off the back of the car, when the car was moving forward, this beam of light, a ball would actually just drop. How fast will this beam of light be moving? And let's say there was somebody over here observing it. Turns out that if this observer were to ask how fast is this beam of light is moving away, not at 2c, but at c, the speed of light. And to this person, that beam of light's coming at c. And the point is, the speed of light is an absolute constant, and it never, ever changes. That is an amazing, amazing idea. In fact, the theory that we come from this is called the theory of relativity. Initially, Einstein wanted to name it the theory of constancy, because he said the one constant in the universe is the speed of light. So let me just summarize. If you're moving towards somebody and you shine a beam of light at them, that beam of light does not get to them any quicker than if the two of you were stationary. Even if you're traveling toward each other, if you're traveling towards someone at the speed of light, this will even make it more clear. You're traveling at the speed of light, and this person is traveling at the speed of light. How fast are you coming toward each other? And the answer is at c, not 2c. You're coming at the speed of light. Now, how do we explain that? Well, Einstein explained it. First of all, he took Michelson-Morley's experiment at exactly what it said. And he said, somehow I need to do something different. So Einstein proposed a solution. And before we do that, I need to give you Einstein's postulates. Einstein's postulates. First one, all physical laws are the same in any frame of reference. And frame of reference again means wherever you are that is moving. So what he said is, let's say you were in a box and this box is moving and you decide to do an experiment. You decide to check F equals ma, or you decide to find out a momentum experiment. You decide you want to find out if m1 v1 is really equal to m2 v2. Or you want to do an experiment on that. Whatever the experiment would be, it doesn't matter that you're moving. Same frame of reference, different frames of reference, all the physical laws will be the same. And then the second one was this: all measurements of the velocity of light will always, I've already said this, but will always give the same value regardless of the motion of the source or the observer. I'm not a big student of Einstein, but what I have noticed about Einstein that is somewhat unique, I think, is that he would take an experiment and he would trust the experiment. He trusted Michelson-Morley experiment. He said, well, then there's no ether. And apparently the speed of light is a constant. It never changes. Doesn't matter what your motion is. It's always going to remain the same. Whereas most people couldn't wrap their mind around that, he accepted that and said, how do I remake the universe to make this work? So that's what I want to show you next, and then we'll get into some of the ideas. So imagine that we have we have a person. I just want to say we have a let's say we have a ball and we have a person here, and we drop this ball on this person. But we also have an observer, and that this is moving at a particular speed. Okay? In a period of time that it takes that ball to drop, this person will have moved from here to here. So this is position A, position B. To this person, this ball will look like it goes like that. Now, that's not exactly right because it would be falling faster at the beginning, but just it makes the math a little bit easier here. In other words, all three of these have motions. And what we would say if we called this sy, and we called this s, and we called this the motion of the ball, we would have this equation. Sy squared plus s squared equals sb squared. All right, just the Pythagorean theorem. But now, let me change the scenario. Let's say that this person right here, this is a light, and we turn this light on, and we have an observer here, and this is moving again at some velocity. We're going to call this sy. We're going to call this distance s for that person. And this we're going to call sc for the speed of light. Now, what's interesting here is that this person would see the speed of light, and this person would see light going here. But both of them would observe light going at the same speed, even though this distance is longer. So speed if that's the speed, speed is, or that's actually the distance. Speed is, in this case, and let me redraw this triangle because I have something I want you to see. But let's say that this is c, and this is the time that this observer experiences, and this is the velocity of the plane. I mean, velocity times time, and this is the actual speed of light times t for this person sitting out here. All right. This is because these are distances. So we know the light travels at the speed of light times t0. We know that the speed of light is traveling, and this person sees this. And we know that all of these distances are the same. And Einstein said, how in the world do I make sense of that? And what he did was that he solved that triangle. And he said, let's say we take ct0, not 0, squared plus vt squared. That's the velocity of the frame of reference. And that's equal to ct squared. So let's do this. C squared t naught squared plus v squared t squared equals c squared t squared. And then he moved this over. By the way, notice it's just simple geometry at this point. And he factored out t squared here, and he got c squared minus v squared. By the way, this is the speed that this car is going by relative to the observer. And then he divided both sides. And what he found was, and we're going to do a little math real quickly here, this is over 1 minus v squared over c squared. Now, you might say, how in the world did you do, I did this backwards here. I'm sorry. So he did this. He said t squared is equal to c squared t naught squared over c squared minus v squared. And solving that, you get this. Trust me on this. You can work out the math. You get c squared minus v squared on the bottom. No, 1 minus v squared over c squared. I'm trying to do this fast, but we can work that out. And finally, we come up with this if we take the square root of both sides. Right? So, this equation is called the time dilation equation. And we'll talk about that more in the next video, but here's what it's trying to tell you. To this person here watching, the person who's watching this go by, the time that is taking place for this person is actually less. If you look at this, v squared over c squared, if I was to put in like half the speed of light, so this was 0.5, we'd end up with 1 minus 0.5, 0.5 squared root of 0.5, 0.25. This would end up that time for one person is different for time for the other person. Let me say that again. And in fact, let me make it even more specific. Let's say that this person here has a stopwatch, and this person here has a stopwatch, and this is going by at 1/4 the speed of, or 1/2 the speed of light. Then t here will be t0 over the square root of 1 minus 0.5 c squared over c squared, which would be t0 over the square root of 0.5, which is t0 over 0.25, and this would be 4t0. What will happen is this. If this guy has a clock, and let's say it takes 4 minutes, well, let's say 4 hours for this guy to pass by. So we go 4 hours. This man's clock will only go 1 hour. 1 hour will take place during the time for this person that 4 hours takes place. But, and here is the really bizarre thing, because frames of reference are, it doesn't matter what the frame of reference is. If I don't know which one of these are moving, to this person, this person's clock will slow down, and to this person, his clock will be running normally. In other words, time adjusts. And that is one of the key ideas behind Einstein's theory of relativity, that time is not a constant. So let me just summarize it. I know we went through a lot. I have something for you to read and some questions answered, and I'm kind of summarizing what we're reading. What Einstein said was this: if speed is constant, speed essentially is distance divided by time. And what Einstein said is that if the speed of light, this number never changes, then these two numbers must be flexible. In other words, what we always assumed was a constant, which is time, is actually not a constant. It's like our Pythagorean theorem we talked about at the beginning. The only reason the Pythagorean theorem always works is because you're always using right triangles. But when we have something that is moving very fast, something close to relativistic speeds, anything higher than about 1/10 the speed of light, all of a sudden there's going to start to be a difference in the way two clocks run. So time is not constant. Space, distance is not constant, but the speed of light is constant. So we'll talk about some of the implications of that in the next video.